afternoon. Welcome back. I feel like I'm a YouTube ad and you guys forgot to pay for premium. My Duolingo premium prescription went off today, so you know how I'm feeling. But after that lunch, I'm feeling amazing. And I hope you are too, and you're ready to ask inquisitive questions. So what we're going to have now is a hot seat. I just made that up, literally right now. But it sounds really good. Okay, so we're going to have fellow scholars that are going to present their work. And how it's going to go is they'll present for a period of time, and then we'll open up the questions to alumni. We have very esteemed guests with us, our former chairperson. It's only fitting, right? And then open up the questions to the rest of the group. Okay, so we're going to have that, and we're going to do it per speaker. Okay, the presenter is going to come up, introduce themselves, tell us something about themselves, and then we're going to go from there. We'll be helping you guys with mics on the side, and as always, you are welcome to go to the bathroom. Just make sure that you don't cause big disruptions. No one walking through the middle because it obstructs the camera view. Just go throughout the side, and then you need to go out throughout the back and not through the front. Okay, thank you so much, and good luck to you.
Good day, esteemed colleagues. I just want to make sure that everyone can hear me, because I can hear myself. Can everyone hear me? Okay, great. My name is Joy Mate, and I am a master's student in chemical engineering, currently specializing in bioreaction engineering. And today, I will be presenting my thesis project. I would like to introduce this topic by discussing the elements nitrogen, phosphorus, and carbon and their relevance in human life and nature. Nitrogen is a key building block in DNA and is a major nutrient in most fertilizers. Phosphorus is known as a limiting nutrient in most plant systems and is instrumental in the production of ATP, which is used in cell development in both humans and plants. Carbon is the chemical backbone of all life on Earth and is present in all organic materials, and is also prevalent in its inorganic form of carbon dioxide. All these elements exist in cycles in nature, which makes sure that these nutrients are assimilated as and when they should be, and also recycled so that they can be used at a later stage. In other words, we can refer to this as Mother Nature's perfect harmony. However, when these nutrients exist in excess quantities, they can cause catastrophic damages to the environment. Nitrogen and phosphorus pollute bodies of water and cause eutrophication, wherein algal blooms grow, which reduces biodiversity in bodies of water and harms aquatic life. An increase or whatever carbon isn't captured in the carbon cycle is converted to carbon dioxide, which increases greenhouse gas emissions and causes climate change. The increased amount of CO2 in the atmosphere also causes ocean waters to become acidified due to a chemical process that releases carbonic acid into marine waters. Therefore, since we have identified that these nutrients can be a problem, how can we go about fixing this? The major contributor to nutrient pollution is waste in its various forms, such as agricultural runoff and landfills, to name a few. By implementing a solution such as anaerobic digestion, which is taking organic matter and breaking it down by microorganisms in an oxygen-free environment, we can combat this problem of nutrient pollution. This process is generally used in waste disposal, but has also become a major contributor to biogas production in some European countries. However, the methane-rich biogas is not the only viable byproduct of this process, as we also get digestate in both its solid and liquid forms is used as an organic fertilizer. In soil-based agriculture, solid digestate is used as compost material as well as matter for grow beds. However, it is kind of limited in its applications in the sense that it can only be used in one form of agriculture. Whereas liquid digestate, on the other hand, can be used in both soil and soil-less agriculture and is generally preferred by farmers due to its ease of handling as well as potential to mix with herbicides. Now, given all of this that has been discussed, there's an important term that we need to consider: hydroponics. hydroponics has gained increase in traction over recent years because of the fact that it is friendlier to the environment. And I will prove this to you by showing you some stats. Soil agriculture takes up to 70% of global freshwater usage, whereas it takes 90% less water to grow a single plant hydroponically than is needed to grow the same plant in soil. There is also a greater control of effluent streams in hydroponic systems, which aids in nutrient recovery, deterring nutrient pollution. And hydroponic systems also have a 20 to 25% higher yield than soil agriculture. Given all of this information, then we can start formulating a process that will aid in nutrient recovery. A crucial step in this process is aerobic digestion, which is primarily used in wastewater treatment for the oxidation of organic matter to carbon dioxide and nitrogen gas. Polishing is used as a final step in anaerobic digestion used in wastewater treatment to improve the quality of effluent before it is released into normal streams of water. However, in this process, we'll be modifying the polishing treatment to remove organic carbon while retaining nitrogen. You may ask why this is important. In general, plants prefer nitrogen in the form of nitrate as opposed to nitrogen in the form of ammonium. And liquid digestate is very rich in ammonium nitrogen. Therefore, it is necessary to implement a nitrification step, which is the oxidation of ammonium to nitrate carried out by chem-autotrophic nitrifiers that feed on inorganic sources of carbon, such as carbon dioxide. However, the decomposers present in liquid digestate feed on organic matter, and since there is an abundance of organic matter in liquid digestate, these microorganisms outcompete the nitrifiers and then in hydroponic systems grow and adhere to the roots of the plants, therefore forming a biofilm which inhibits nutrient uptake by the plants. Therefore, illustrating this, we can now come up with a process that will take us from waste to food by starting with anaerobic digestion, followed by aerobic digestion, nitrification, and then finally hydroponics. Given all that has been said, let us now look at the analysis of the investigation of the effect of pH on the aerobic polishing of liquid digestate. As we continue, this is some important terminology that you just need to be aware of because it will come up quite often. Chemical oxygen demand is the measure of the chemically oxidizable material present in any given sample, and the theoretical oxygen demand is the amount of oxygen needed to oxidize ammonium to nitrate, as shown in the formula. These are the variables which are kept constant throughout all the runs in the experiment in order to obtain or to sustain mesophilic conditions for the bacteria present in the reactor. These are the measurements of the essential nutrients as previously discussed, where the COD is used to infer the amount of carbon present in the system. Let's get into the results. This figure shows the profiles of the nitrate concentration depletion over the reactor runtime of 10 days. The decrease in the nitrate concentration is evidence to the lack of nitrification taking place in the reactor, and also the assimilation of nitrate by the microbes. It can also be observed that the pH 6 run shows the largest decrease in nitrate concentration. This is the profile for the phosphate concentration, and in the first day, the profiles are identical. However, from the second day, larger differences are observed in the data. The phosphate that is present in the liquid is converted to ATP, which is used for cell growth as well as cell maintenance, which explains the decrease in the phosphate concentration over time. It is also important to note that growth requires a lot more energy in terms of ATP than cell maintenance. And finally, we have our ammonium concentration, which, apart from the organic carbon, is the largest contributor to nutrients in the entire system, where the concentration is 10 times that of the nitrate and the phosphate. Over the first 5 days, the profiles are seemingly identical. However, thereafter, pH 8 shows a substantial increase in ammonium concentration. This is due to a chemical process called ammonification, where microbes convert dead biomass into ammonium or inorganic forms such as ammonium. This graph is actually my favorite because it shows the comparison of the actual COD and the theoretical oxygen demand derived from ammonium. This graph shows that although the pH 6 has the largest decrease of COD, where finally the actual COD is less than the theoretical oxygen demand, it has also been seen in previous runs that pH 6 has also lost the highest amount of nutrients consistently. Therefore, because the pH 8 run also has the highest amount of retained nutrients, it is the favorite pH to proceed with in subsequent experiments. Now, given all the results that have been presented, we can conclude the following. Using aerobic digestion in an excess oxygen environment, we can continuously and effectively remove organic carbon while retaining some form of nutrients by implementing a polishing system. In future, this system can be improved by implementing a fed batch type of system to improve nutrient retention by operating the cell maintenance regime as opposed to the growth regime. Also, this process also shows that by using something as simple as recycling waste that causes harmful nutrient pollution, we can use modified organic processes to sustainably and renewably produce food and, to a larger extent, energy and water. Thank you, esteemed colleagues, for your time, and I would like to extend a special thanks to the MasterCard Foundation Scholars Program, as well as the University of Pretoria, for giving me this opportunity to share my research. Thank you as well to all the esteemed guests who have listened to my talk.
Testing. Almost there. We're now opening the floor to questions. We're first going to start with our esteemed colleagues, alumni, and the professors, and then we're going to open up to the rest of the floor. So the floor is yours, former chairperson.
Okay. Thank you. This was a very great presentation. You show good knowledge of what you're doing, and this is a very interesting area because that's where energy transition is just energy, and anything that can actually reduce climate change is increasingly important in data. But the question now is, I have two questions. First, is this research, your research, is it an honors research, or is it a mini dissertation, or what kind of research is it? And if it is not an honors research, what has not been said about, what you're saying now that you're going to say? In essence, what have they said, they, other authors, and what are you about to say that has not really been said before or has not been said in a certain way?
Thank you very much for the question. It is a very good question. So this project, I began it in my honors year, and this is now my thesis project for my master's. And you raise a very good point in terms of whether or not there is a gap in literature for this type of work. In doing the research, formulating my literature review, I noticed that a lot of processes that deal with digestate, especially liquid digestate, focus only on going from using liquid digestate straight into a hydroponic system. We, in our lab, have seen the effects of having organic matter present in hydroponic systems. And we've seen the ill effects that it has on the roots, the deterred quality, and the overall, it's not good for the plants. Therefore, I know that aerobic digestion of liquid digestate is not something that I've seen in literature. I know that there is a gap. That's why that I'm confident that this work will be able to gain a space and contribute beneficially to the field.
Okay, thank you, that's great. But again, just go about like make more further research to
Yes.
be very sure.
Yes.
So that if there's room for collaboration and all of that, you can come up
Definitely.
with something.
I think what I just presented today was kind of a scaled down version of what I've been working on because there is a lot of information. I just didn't have time to share all of it. Yes. Yes. ma'am.
Yeah, okay. Thanks very much for your presentation. I was able to follow. However, I just like to find out about your findings.
Yes.
You mentioned towards the end that pH 6
Yes.
was less in terms of producing nutrients, and in relation to pH 8. Why is that?
Oh, yes. So the basis for that is, I don't know if I can go back to the graphs just to illustrate this, but in all the data, I saw that pH 8 consistently showed the largest amount of loss of nutrients over the runtime of the reactors. So we'll see in the ammonium, they all start at the same concentration, but pH 8, pH 6 ends up down there. Same as pH 7, but in this run as well, pH 6 is also the lowest at the end. In this run, pH 6 is also the lowest at the end. So in terms of nutrient recovery, pH 6 doesn't really help me with that. Yes, it does remove carbon, but my goal is ultimately nutrient retention because I would like to use those nutrients as a fertilizer for a hydroponic system.
But what could be the explanation for?
For the differences, I believe that in the different regimes, they put stress on the microbes. The microbes primarily do best at a pH of 7. However, at a pH of 6, where it's borderline, bordering on acidic conditions, they have a lot of stress and then tend to take up a lot more nutrients so that they can just stay alive and not die off. That's why I also don't see an increase in ammonium concentration at the end because, you know, they're not in the cell. None of them are, they just keep growing or something.
Can I have a question?
Sorry, yes.
Thanks. No, I just like to find out about the process that you used,
Yes,
you
ma'am.
applied in your study. Has it been utilized anywhere in the world for any other purpose, or you were the first people to implement that? Fishing.
As I was saying to the previous speaker, I haven't seen any implementation of aerobic digestion in this form. Aerobic digestion, from what I've seen in literature, has been used in wastewater in different forms to completely remove nutrients, not to retain nutrients. So from a point of nutrient retention, I think I've, kind of got a bit of an edge on them.
Hello, that was a
Hello.
great presentation, and your slides look very good. They are not messy and all that. And I'm going to ask you a question just because this is a training platform. We're preparing you for greater things. Research comes up with new knowledge or novel knowledge, and that translates into tangible products that impact society. And you had the answers to a question that I asked you, but I just want to ask you so that you can be able to answer that and maybe add on to that. What are the key areas that your study will impact at the end?
So, okay. My study, primarily my study, will definitely impact the food industry. And as I previously illustrated, to a larger extent, it will also affect energy and water. Energy by means of anaerobic digestion, as I've previously discussed, is a major contributor to biogas production. The biogas from anaerobic digestion is very rich in methane and will therefore, provide to sustainable energy production. Water, although this, I did not discuss it directly in this project, by using a process called phytoremediation, especially using aquatic plants, you can take hydroponic waste and simply let aquatic plants grow in this water, which will absorb all of the nutrients that are excess or that haven't been taken up by the plants, which will ultimately provide you with clean water at the end. So my project, although it directly deals with food, to a large extent, as part of the entire process that I've described, will also deal with energy as well as water.
And maybe you can also add that it will have an economic impact and also research now is supposed to benefit communities, so the education arm should also be included, so that you train the communities about renewable energy, about recycling as well.
Okay, thank you, ma'am.